Hey guys, welcome back, and this week's video is going to be about identity functions. And I feel that often we tend to skip over this part, or for example, I know I never really got taught this or got this explained, but it comes back subtly, but it's quite important, and that's why I wanted to make a video about it. So let's start off with what is an identity function. An identity function is basically a function for which your input is your output. So we are represented with y of x is going to equal to x. For example, I of 3 is going to be 3. I of sine 30 is going to be sine 30. I of e to the power of pi is going to be e to the power of pi. Your input is always your output. Graphically represented, your identity function is just your very simple y equals x, where it's a straight line and your y value is always equal to your x value. Your input is always equal to your output. Now, why might this identity function be important? Well, here are just a few properties that we can derive from it. If we have a function and we take the input to be the identity function, we will just simply end up having our function. And this might sound a bit theoretical or useless, but you'll see in a minute why this actually is of importance. Because remember, I of x is simply x. So f of I of x is going to be x. So whenever you're taking a composite function of an identity function, you just have your original function. Secondly, if you take the composite function and your outer function is an identity function, but your inner function is your actual function, you're just going to end up with your inner function. Why? Because I of x is equal to x, so I of f of x is going to be your input, which is f of x. You always end up with your input as your output. And another way that we can use this is for inverse functions, and let me show you what I mean. So if you take a composite function of original function and of the inverse, you're going to end up with an identity function, so you're going to end up with x. So what I'm trying to say is, and this works in both ways, either your outer function is the inverse and your inner function is the original function, or your outer function is the original function and your inner function is the inverse. In the end, when you take these composite functions, you will always end up with x. And this might seem intuitive because you're basically undoing the inverse or undoing the original function. But I'm going to show you just in a second why this makes sense if you are struggling to wrap your head around it. So why the previous two statements that I made about inverse functions and original functions make sense is for the following reasons. In your original function, you have an output for which you put an input into your function to get that output, right? Basic f of x is equal to y. Your inverse function is you're putting in the output into the inverse function to get the input of the original function, right? And in our first case, where our outer function is the inverse and our inner function is the original function, we have x as the input, f of x is going to be our output, right? F of x, f of input is output. And if we take the inverse of the output, we end up with the input. And input, in this case, was x. And that's why that statement makes sense. Now, second example, a bit different. In this case, our x is actually our output because we're taking the inverse function, and in the inverse function, the x is the output. And then the inverse of the output is going to be the input. So this altogether is going to be the input. And f of input is going to be output. And we end up with an output. And again, x was output, so we end up with x. So I know that this might seem a bit confusing with all the inputs, outputs, blah, 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 but I hope you're getting your head around it, and I hope it makes quite intuitive sense. If not, just listen again carefully And remember that in different cases, we have different x's. In one case, x is the input, in other case, x is the output. But in both cases, our value is whatever x is. So taking the composite function will just result in x. So both of these are identity functions. So where might we use the following properties or identities that we have identified over here? Well, mainly we use them to cancel out composite functions, and let me show you what I mean by that. So let's say we have f of h is equal to g, right? And we want to find h in terms of f and g. So the first thing is, remember back to these properties right here. We're going to take the inverse of f of both sides because we want to isolate h, and let me show you where this gets us. If you think back to what we've just said, this right here is going to be an identity function. What this also means is if we're taking the identity function of h, it's going to simply be h because our input is our output again. So h is going to equal to the inverse of f of g. That's simple. And before, you might have looked at this and were a bit unsure, like, what do I do? How do I act? How can I cancel things out? But here we see why this makes perfect sense. Another example is where we have f of h is equal to g, same thing, but now we want to find f in terms of g and h. And in this case, try it for yourself, see how far you get, but if not, in this case, we're going to focus on the inside of the function. Here we focus on the outside of the function, but here we're going to focus on the inside of the function. And we're going to take f of h of the inverse of h is equal to g of the inverse of h. And again, recognize that this right here is going to be an identity function. What this means is going to equal to x. So f of an identity function is going to equal to f of x is going to equal to f in this case, right? And now we have that f is equals to g of the inverse of h, and that's our final answer. Now, last example is we have f of h of g is equal to k, and we want to express h in terms of f, h, and k. And in this case, we have to apply both our previous steps of manipulating the inside and the outside of the function because h is right in the middle. So you can start off with anything, but I will start off with the outside. And I'm going to take the inverse of both sides. Again, spotting that this right here is going to be an identity function. So we're gonna have an identity function of h of g, which is just going to be equal to h of g. So now we can say that h of g is equal to f inverse of k. Now, focusing on the inside, we're gonna take the composite function of both sides of the inverse of g. And here we spot that this is an identity function, meaning that we have h of an identity function, which means h of x, which just means h in this case. So we're going to have h is equal to the inverse of f of k of the inverse of g. And this is going to be our final answer. Obviously, I feel like the notation could get confusing and you're better off writing it like this, but obviously both are true. I'm just showing you, if you're maybe not familiar with this notation, that you can also write it using the following notation, as goes for all cases. So I hope you enjoyed. I hope you now see why such a basic function is, it seems insignificant, so often we skip over it, but how this simple straight line can come back in very significant use in making equations such as these so much more easier by manipulating the outside or the inside of composite functions. So I hope you enjoyed, and see you next week.